This is just an informal video tour of DHLS, which is a high-level synthesis program that I've been working on that synthesizes LLVM functions into Verilog. And well, this is an experiment in documentation, and this video is current as of January 3rd, 2019. So if you look in the README, there's a link to the most recent source code video tour, build instructions, the dependencies, just some basic information about the structure of the project. And then if you look at the actual project files, there's a source directory and a test directory. There's, some boilerplate like the gitignore, the Travis script, the CMake lists. And then there's a bunch of Verilog files, and these are all handwritten Verilog files that I use to test Verilog that's generated during unit testing of the system. So like these rams or handwritten ram types, there's the README. And then all these things with _tb.v are actually test benches that I wrote to test modules that are generated by the system during unit testing. So compare greater than TB, for example, we define an assert macro that's used in the test, and then here's the actual test module. And basically we're just, running a bunch of clock edges and seeing what data comes out of our test modules. And the test modules are, this compare greater than module, and if you look around you won't see it because it's actually automatically generated during unit test running. And then there's this RAM module, which is one of the handwritten RAMs. This is RAM2, which I use in testing of all of the generated code. Here's the RAM2 module itself. So yeah, I should really refactor this so that these are all in their own directory, but I haven't gotten around to that yet. And then if you go into the test directory, there's a bunch of different files. Dependence is actually just sort of a playground, and so you can ignore that. And then there's test utils, which is just a bunch of utility code to run Icarus Verilog and load files. And then there's the LL files, and these are all C programs and some .ll programs, which stands for LLVM bitcode. And these are actually the some of the C programs that are used in the unit tests themselves. So for example, here's a C program, excuse me, that is synthesized in the unit tests. And then the major thing in the unit test is scheduling.cpp. Oh, actually, so catch.hpp is just the testing framework. Scheduling.cpp is the actual unit test. So it's basically a bunch of stuff like, for example, here's schedule a single store operation. And as you can see, this load module function for load single store actually loads the program LL files underscore or a slash single store. So it actually loads this program and synthesizes it. And the formats of all the tests are pretty similar. So in the single store program, we basically load an LLVM module that contains single store. We get the single store function, print it out, create some hardware constraints, schedule the function, check some things about the schedule, create what's called a state transition graph, and then emit Verilog and test it. And pretty much all of the test cases follow that script, and they're pretty uninteresting unless you're the actual script is pretty uninteresting. It's more the details of the program that you can look at that are interesting. And there's a bunch of different ones of varying complexity, matrix vector multiply. There's some tests that use pipelining and things like that too. But you can look in the LL files to get an idea of what kinds of programs can be synthesized. And then the actual source directory contains the system. So algorithm.h is just a helper utility function that I use in all my C++ projects. And LLVM codegen is just some wrapper functions to make it easier to generate LLVM. So some of the programs I use in unit testing are written as C and then compiled with Clang, and others I just build in LLVM directly, and that's some utilities for it. And then scheduling.h is actually the meat of the program. Well, the scheduling files and the Verilog backend files are the meat of the program. And then utils is just a bunch of like text generation stuff, and some boilerplate kind of commonly used LLVM functions. So scheduling.h is the biggest, is sort of the front end of the system, basically, right? So it's got descriptions of basically what memories are like, what kinds of operations are supported currently in the high-level synthesis program. It's got, defines the hardware constraints, a bunch of different things about memory. And then here's the actual schedule class, which is basically just a bunch of numbers that represent the start and end execution times of different instructions. And then there's a bunch of functions to create schedules, a bunch of stuff for representing state transitions. For example, here's the state transition class for the finite state machine that gets generated, the STG. Here's a representation of a pipeline because the system can pipeline loops. And here's the state transition graph, which is basically just an explicit representation of a finite state machine that comes out of the scheduler, and it's usually abbreviated as STG. So the typical flow in scheduling is like we saw in that unit test. You create some constraints, some hardware constraints, and you load your LLVM function that you want to synthesize, and then you use the schedule function to create a schedule. And then once you've created a schedule, then you use build stg to create an explicit finite state machine or a state transition graph out of the function and the schedule. And then you go on to emit Verilog. So in Verilog backend, which is what the name suggests, it's the code that takes the state transition graph and converts it into Verilog. You've got basically, well, I've got a bunch of kind of janky classes that represent different objects in Verilog, like always blocks and module instances. And then the description of functional units, which is stuff like adders and multipliers and things like that. Here's a more elaborated description of a pipeline that contains more details about the pipeline and the names of the variables that are used. Descriptions of RAMs, options for the architecture. There's this microarchitecture class, which is kind of a disorganized catch-all class that sits in between a finite state machine and an explicit Verilog description of the generated hardware. And then there's a bunch of stuff for making it easier to generate test benches automatically that I use in the unit tests. And the general flow is once you've got your STG created through scheduling, what you're going to do is you're going to use the build microarchitecture function to build a microarchitecture out of the state transition graph. And once you've got a microarchitecture, what you're going to do is emit Verilog, and you'll see that in the test cases too. And there's a zillion different flavors of these functions, but they all pretty much do the same thing. So yeah, the general flow, which you'll see in all the unit tests, is you create an LLVM function in some way, whether it's through C++ declining to LLVM or just writing in an LLVM manually. And then once you've got that, let me just look at another example, right? And once you've got that, basically what you'll do is, you'll create the function, you'll create with some hardware constraints, then you'll schedule the function, build the state transition graph, build a microarchitecture from the state transition graph, and then emit Verilog for the microarchitecture. And that's pretty much the flow of the whole system. So take a look at the rest of the repo, and if you have comments or questions, let me know in the issues. And if you like this repo, please give it a star.